In this practical session, you will learn about EMF. EMF is an electromotive force which produces the potential difference across two open-circuited ends of a conductor. Let us take a conducting wire, a horseshoe magnet, and a galvanometer. Now, let us conduct test number 1. Connect the galvanometer across the ends of the wire. Magnetic field lines are present between the two poles of the magnet. Cut the magnetic field with the conducting wire in a downward direction. You will see that the galvanometer shows deflection in a clockwise direction. What is deflection? Is it persisting or temporary? Let's check once again. The deflection is there only when the wire is moving. Once the movement stops, the deflection ceases. This observation is very important. Next, let us conduct test number 2. Move the wire towards the upward direction. You will now see that the galvanometer shows temporary deflection only when the wire is on movement, but the galvanometer pointer moves in an anti-clockwise direction. What do you infer from these? Firstly, when the wire cuts the magnetic field, EMF is induced in the wire, causing a current flow through the wire. Secondly, the direction of current flow in the galvanometer depends on the direction of motion of the wire in the magnetic field. Now, let's conduct test number 3. Fix the wire arrangement constant and move the magnet in an upward direction. We observe that the galvanometer again shows temporary deflection in the clockwise direction. Now, let's move to test number 4. Fix the wire and move the magnet in a downward direction. We notice that the galvanometer deflects temporarily in an anti-clockwise direction. We infer that whether the wire is moved or the field is moved, EMF is induced in the wire. This concept was established by Faraday and is called Faraday's first law. Faraday's first law states that whenever there is a change in the magnetic flux linked with the circuit, an EMF is always induced in it. In other words, it can be stated that whenever a conductor cuts magnetic flux, an EMF is induced. Now, let's change the position of the poles of the magnet by just rotating it. Let's repeat test number 1. You now see that the galvanometer deflects temporarily in an anti-clockwise direction. When compared to test number 1, we observe that the galvanometer deflects in the opposite direction due to changing the polarity of the magnet. Similarly, let us repeat the other tests and change the polarity of the magnet. Now, repeat test number 2. Observe that the galvanometer deflects temporarily in a clockwise direction. Now, let's repeat test number 3 and observe the effects. We notice that the meter deflects temporarily in the anti-clockwise direction. Now let's repeat test number 4. The galvanometer deflects temporarily in the clockwise direction. We have now observed that the direction of deflection changes when the poles of the magnet change. Thus, the direction of current flow in the galvanometer depends also on the direction of the magnetic field. This concept was stated by Flemings in his right-hand rule. Now, let's see how we can increase the magnitude of the induced EMF. Repeat the 4 tests, but cut the magnetic field with the wire in high velocity. We now observe that the galvanometer deflects more than in the previous tests. It indicates that the magnitude of the induced EMF increases when the flux change increases. This phenomenon is stated by Faraday in his second law. The second law states that the magnitude of the induced EMF is equal to the rate of change of flux linkages.